Okay, let's go ahead and get started on the next problem, just another problem to practice. Again, this is a problem that we already discussed last class when we set up our hypothesis. Um, Take about half a minute to read the problem on your own before I get started. So the first statement gives you a broad picture. You want to test how much the sweetness of a new cola drink is affected by storage. And then it goes into the meat of the matter. And this is where the idea lies, the sweetness loss due to storage. So in essence, you are saying that after storage, you have a loss in sweetness. Was evaluated by 10 professional tasters by comparing the sweetness before and after storage. Okay, so based on the results, does storage affect sweetness? Okay, so to visualize what is going on here, you have a certain set of data for sweetness before. So you have all of these 10 testers who have tasted a cola drink and put in a value for sweetness before storage. Then you put that cola through storage, and then you again taste those drinks for sweetness after storage. Okay, so if you really look at the mean sweetness from the first column, let's say this is mean sweetness before, and this is mean sweetness after, right? After storage. So going back to the question, we are talking about sweetness loss, which basically means that between the mu before and the mu after, which one is expected to be bigger? Before or after? The before mean sweetness is expected to be bigger, right? Because that's when you can feel that there is a sweetness loss, right? So the question is, based on the results, does storage affect sweetness? So in essence, you have two possible hypotheses you can frame from here. One is, yes, storage affects sweetness. The other is, storage does not affect sweetness. When does storage affect sweetness? So if I say storage affects sweetness, when does that happen mathematically in terms of mu B and mu A? When will storage affect sweetness? When, very good. So you can say that mu A less than mu B, right? It's the same thing as saying mu B greater than mu A, right? Yes, no? So mu A less than mu B. In other words, you can also say that mu A minus mu B is less than 0, right? It's just rearranging that equation. Recall we discussed this in our last class. It's basically putting values on one side of the equation and the variables on the other side. So that difference in sweetness is what you're capturing. Following? Yes, no? I don't hear a yes. So equal sign, inequality, equality, it's the same concept of basic equations, right? So if I say that x minus 3 equals y, can I say that x minus y equals 3? Yes, no? Right? So all I do is just bring that y here and bring that -3 to the other end of the equal sign, right? It's the same thing I'm doing here. Okay? Think about this as an equality sign. Only in this case, instead of equal, it's less than. Okay? So x less than y means x minus y is less than 0. All I have done is just shifted it. Yes, Amy. Well, I have used the after as the first marker here, as you can see. So if my sweetness after storage is less than the sweetness before storage, only then I can say there is a sweetness loss, right? Right? Isabel, where did I lose you? See, this is the part that I miss when I am. So when you say storage affects sweetness, this is when the mean difference is less than 0. Everybody is with me on this? And I'm capturing this difference as an after minus before. If I was doing this as before minus after, it would have been greater than 0, right? And I'm still not sure which one is the right way to do it. Depends on how the data was captured, right? So the other end of the spectrum is storage does not affect sweetness, which is when your mu difference is greater than equal to 0. One more time. The way we define the problem dictates the way we state the hypothesis. The problem is talking about sweetness loss, which basically tells you that after storage, you have a reduction in sweetness. So the before minus after, or the after minus before, irrespective of whichever way you look at it, it gives you the same understanding. Okay, there is a reduction in sweetness. And so you say mu difference is less than 0. The difference at after minus before is less than 0. There is a difference or reduction in sweetness. Only when you are able to do that, you can say that storage affects sweetness, right? And therefore, the other end of the spectrum is when mu difference is greater than equal to 0. Of course, the upper one becomes your null hypothesis because of the equal sign, and the lower one is your alternative hypothesis. Still with me? Yes, no? What is the next step? If I give you this problem to do in class or as an exam, how would you, what would your logical next step be? Yes, find the critical value. To find the critical value, what is important for you to ensure that you're on the right track towards finding the critical value? The confidence level is 5%. If nothing is given to you, it's an alpha of 5%. That's how you go with. What's the next step in the process? Simple. Keep it simple. You visualize it. Okay? Because that visualization leads you to understand where your rejection is. Now you've already framed your hypothesis. Now you visualize the process. This is your null hypothesis distribution. This is 0, hypothesized value. If it's greater than equal to 0, then it is your null hypothesis. So when are you rejecting it? When it's less than 0, according to your hypothesis. When are you rejecting it? When it's less than 0, right? So your entire rejection of 5% is on your left tail. Right? Your entire rejection of 5% is on your left tail. Now, Sarah, as you said, you can now formulate the corresponding critical value. And if this is how you have drawn your hypothesis, David, again, this is a t-test, right? There is no information on population standard deviation. So sigma is not present. It's a t-test. So your t critical is based off of the degrees of freedom and your cumulative probability, right? So your critical value is based off of 9 degrees of freedom because you have data from 10 professional tasters. Yes, no? And of course, you are looking into a 0.05, or which is a 95% on the other side, just the way we did it before. But we'll do everything by Excel. I'm just giving you the idea of where the critical comes from. So from your Blackboard, you'll find another data set called Sweet Cola. Okay, let's open the data set. Oops. Okay. I thought I have lost it for a second. So here is the fun part. There are 10 data points here that captures sweet loss, okay, or sweetness loss. Most of these numbers are positive or negative. Positive. What does it tell you in terms of how loss has been captured? Is it mu A minus mu B or mu B minus mu A? Sarah? B minus A. So before I confuse anybody, let's go back to our PowerPoint and it could be either way, depending on how the data has been captured, right? So in this case, all it's saying is if mu B greater than mu A, then there is a sweetness loss. So the mean difference is mu B minus mu A is greater than 0. In other words, mu difference is greater than 0, and this is less than equal to 0, which basically means that it's still a one-tailed test, except all of your rejection happens on the other end, because now your rejection is when mu is greater than 0. Because now we can then compare this with the sample data much more clearly. Okay, it is just how the sample has been drawn. The sample has been collected as a before minus after, which is why you see mostly a positive values. You want the before sweetness to be higher than the after sweetness, right? So the before minus after is in this case greater than 0. So it is just an adjustment based off of the data set that I have. And now I can conduct my t-test in the same exact way that I did the last problem. So what would we do here? What's the next step? It's still a single sample t-test. I really wish that I had the original data in which there was a before data and an after data, and we didn't have to go through any dummy or anything. It was just a simple swap. Okay, pick up those two columns and boom, the answer is there. somewhere there were those two columns, and the calculated column of the difference is what you see here, the sweet loss. So what do you do next? Ping. Create a dummy column again with two values because we want to capture variance in that column. And then you go under data, go under data analysis, choose t-test to sample assuming unequal variances. Hit OK. The first range is the first column. The second range is the second column, column B. What is the hypothesized mean difference? Hypothesized mean difference, Ryan? 0, because that's how we have framed our hypothesis, right? If you look back at your hypothesis, you're looking at that mean difference to be either greater than or less than equal to 0 or something like that, right? So that value is 0. Of course, we have captured labels there. Output in D2 is good. Hit OK. And it provides you your output. Again, we clean this up because we have essentially been too clever with Excel. We have ditched Excel in their own mind game. Okay, we have forcefully created this as a two sample test, even though it's not. So we don't need that dummy anymore. This is not a two sample test. So this is a one sample t-test. And this is not a hypothesized mean difference anymore. It is just your hypothesized mean, which is 0. And the rest of this absolutely falls into place. Now, I was having this conversation in the previous example, and I'll complete this conversation here. So when you have a z value, that is of the x.xx format. Okay. When you have a probability, that is normally of the x.xxxx format. And when you have a t value, the typical norm is it's x.xxx format. So 3 decimal places to the right. That's how you differentiate also between a t value and a z value, that we don't get confused. And if you even look at your t table and compare that with z table, one gives you 3 decimal places, the other gives you 2 decimal places. That's a easy, in my view, I call this idiot proof. Okay, it allows us to not make mistakes, and I do that all the time. Okay, so if I have to look at that stat, I'll just choose the t stat value, the t critical value, and I will convert them into 3 decimal places. I'll look at the probability values, and I'll convert that into 4 decimal places. Now, all of the hard work we did in the slide when we framed our hypothesis was to essentially understand where our rejection is coming. Okay, where are you rejecting? Is it a one-tailed test or a two-tailed test? Sarah Al-Zarani. One-tailed test. Now that we know that, now we can pinpoint on any one of these, not any one, a specific one that caters to the test that I'm looking for. So I'm looking at the p-value of the one-tailed test. That p-value of is 0.0123. What are you comparing your p-value against? P-value less than alpha means you reject your null hypothesis, right? So in this case, your 0.0123, is it less than 0.05? You bet, right? And therefore, you reject your hypothesis, your null hypothesis, and you conclude that, again, I'm looking for a simple statement. that comes straight from your way you framed your hypothesis. When I infer, I say, based off of this data, after I analyze the t-test, I reject the null hypothesis and conclude that, help me complete this sentence, storage affects sweetness. Okay, that's the way you infer back to the problem. That makes it a closed loop approach to problem solving. So this is a classic example of, I think I should be able to call it flawed deductive reasoning. Okay, flawed deductive reasoning being the reason why, because there are too many assumptions in between. Okay, so one is red wine contains polyphenols. That's a fact. Okay, so fact check, yes. Blood cholesterol levels. Okay, so cholesterol, high cholesterol, low cholesterol, risk of heart attack. There is again a maybe scenario there. So you are stretching the, I know people, I'm sure you know people in your knowledge, in your families who have high cholesterol level, lived for 90 years, never had a heart issue. Okay, blood pressure, it's so much of a thing in this country that the moment it goes anything around 120/80, go on medication. But there are people I've known that who have lived with a very different blood pressure, and it's just their level of normalcy. Every human body is unique. And so, there is a lot of assumption in the fact that, okay, if your cholesterol levels change, then it have a chance of heart attack, right? So that's one assumption. Next is um, uh, the polyphenols that will act on these cholesterol levels. And then based off of that, you are making the deductive reasoning that, oh, wine impacts your chance of having a heart attack. And the slightest sniff of that, and the marketing companies go gung-ho, right? So this is our one opportunity to take an upper hand of red wine over whiskey or something else. Okay, and put um, a health spin to it. And suddenly it becomes a hot commodity. And that's the way of life. So to see if moderate red wine consumption increases the average blood level of polyphenols, a group of 9 randomly selected healthy men were assigned to drink a bottle of red wine daily for 2 weeks. Their blood polyphenol levels were assessed before and after the study, and the changes were noted. Okay, so does consumption of red wine protect against heart attacks? Okay, so consumption of red wine, oh, my ink color magically changed from black to red. That's good. Consumption of red wine protects against heart attack. Okay, if that is a hypothesis that I'm going with, how would I frame this in the context of this problem? There is still a before and after here, right? So the mean polyphenol level after should be more than the mean polyphenol level before. Yes, no? Because if my polyphenol level is increasing after the consumption of wine, only then can I say that, maybe it's going to help me reduce heart attack, right? So in this case, again, I'm going by the previous setup, mu A minus mu B is greater than 0, right? Right? This is the same as saying mu A is greater than mu B. A meaning after, B meaning before. Okay, so after consumption of wine, my polyphenol level increases. Ping, am I correct? Okay, so if that is the case, then does not protect will be mu A minus mu B, or the mu difference is less than equal to 0. So that becomes your HO, and this becomes your HA, right? Greater than 0. So one final time. First question. Everybody gets how we frame this hypothesis? Yes, no? Yes? That is the most important part, and I stretch on this every time, because if you get this right, Everything else follows from here. Once you are able to frame the hypothesis correctly, what is the next step? Sarah Al-Zarani. You draw your distribution. Your distribution is for whom? The null or the alternative? The null. So the hypothesized value is 0. When am I rejecting the null hypothesis? When the difference is greater than 0 or less than 0. When am I rejecting it? This is my null, right? So when I'm rejecting it, it's greater than 0, which basically means that all of my rejection falls on the right-hand side. That's my entire 5% chance of rejection. Yes, no? Because once I frame this, then the rest of the story becomes easy. Now I have the data. Now I put it in a software and I figure out what the corresponding tests would be. And based off of that, I do my analysis. But again, as I said before, it will give you everything. If it was a two-tailed test, if it was a one-tailed test, what the actions would be, it'll give you everything. Your job is to figure out which output you want to consider for your final result. And you can never do that unless you know how to frame this hypothesis. Make sense? So now that you know it's a one-tailed test, it's a right-tailed test, your rejection is when it's greater than 0. Now you go back to the wine polyphenol Excel file. Okay. So there is something called the polyphenol change. So from all of those 9 people who did a before test, did an after test, and that change has been recorded. Okay. Again, I am sorry that I have a different kind of a data set. I wish I had the actual data of before after, because that would have allowed you to. So in this case, as an example, and in all these cases that we are talking about in a before after setting, they would be paired t-tests, because you are pairing the same individual and you are recording before and you are recording after. Okay, but in this case, because we are not using those two means, we are using the unequal variance because you are force fitting a dummy variable. I saw the lightning. We create a dummy variable. We go to data, data analysis, t-test sample assuming unequal variances. First range is the polyphenol change. The second one is the dummy. Hypothesized mean difference is again 0 here because that's how we have set up our hypothesis. Levels checked, alpha 0.05, output day 2, hit OK. And again, as I have done in the previous ones, I'll clean this up. I don't really need this dummy anymore. I have gotten what I need. This is not really a 2-sample t-test. It's a 1-sample t-test. This in reality is not a hypothesized mean difference. It's just a hypothesized mean. And if I want to clean this up even more, the t values, I would represent them as 3 decimal places. And the p values, I would represent them as 4 decimal places. That's also another thing. Before I made that change, you saw how it was like, I think it was what, 10 e raised to -5 or something like that. So oftentimes you will come across Excel saying 10 e raised to negative 5, which basically means 10 times 10 raised to negative 5, which basically means 10 divided by 100,000, 5 zeros. And so you essentially take those many decimal places, and that's why the decimal place is like that, 0.0001. Okay. We have already confirmed the fact that this is a one-tailed test. So that's the p-value that I'm looking at. I'm comparing it against an alpha of 0.05. And so what is my conclusion? Do I reject or do I fail to reject the null hypothesis? It's a very clear rejection of the null hypothesis. And so once I reject the null hypothesis, what do I conclude? Red wine does not or does? Why so? When you reject the null hypothesis, what are you going with? Yeah. Yeah. When you reject the null hypothesis, you're basically going with the alternative, right? And the alternative basically tells that red wine protects against heart attacks. As much as these assumptions are flawed, a very similar study was done in all essence. This is exactly what the wine industry did. With statistical proof, they came to the market and says, drink us and you'll stay healthy. Okay, let's take a quick 5-minute break and we'll come back at 8:15.